This is an extension of the standard model of matter, the standard model of particle physics. So in the HSC physics course, there's part of a topic, the very last module, which deals with the standard model of particle physics. Just a refresher. So there are things called quarks. Okay, quarks typically make up protons and neutrons. So there's up and down, charm, strange, top, bottom. There's 6 quarks, okay? They come in 6. Particle physicists like to call them flavors. They come in 6 flavors. 6 flavors of quarks. There's also 6 leptons, so an electron, muon, tau. These are all negatively charged. They've got a charge of -1. And each of these has a partner called a neutrino. So there's an electron neutrino, muon neutrino, and tau neutrino. So there's 6 leptons. Okay, these are the matter particles, the fermions. There are also force particles called bosons, which help mediate the forces between the fermions. They help mediate the interactions. So there's 5 force particles. There's the photon, which carries the electromagnetic force. Okay, so light can be thought of as made up of strings of particles called photons. There are particles called gluons. Okay, so photons and gluons, they've got no charge, they're neutral. Gluons actually mediate the strong force. Okay, these hold the quarks together in protons and neutrons. Okay, there are also the W plus and W minus bosons. These carry the weak force, the weak nuclear force, and they're responsible for radioactive decay. So the reason why the sun shines is because of the energy which comes about from its radioactive processes happening in its core. Okay, and the W just stands for weak. And there's I should say the second last particle. It's called the Z boson. The Z stands for 0. It's got no electric charge, and that also helps. Okay, and the Z boson is used for conservation of momentum. Okay, it's there to conserve momentum, to make sure the numbers come out correct in nuclear reactions. And the last piece of the puzzle, which was discovered in 2012 experimentally, is the Higgs boson, H for Higgs. That's the mass giver. Okay, so these are the bosons. These are the force particles. There's this beautiful, well, in my opinion at least, beautiful mathematical theory, which I believe came about in the 1970s. One of the pioneers was James Gates, Professor James Gates now at the University of Maryland in the United States. In his words, he said that he found one more beautiful balance that we can put in nature. So supersymmetry is this idea which takes the fermions and bosons, so all the known fundamental particles of the standard model of matter, and doubles them. Okay, so twice the amount of particles in the universe, according to supersymmetry. It hasn't been discovered experimentally yet. No particles, as they're called, have shown up in detectors. How does supersymmetry work? Well, okay, so it's a mathematical theory, so supersymmetry, also known as SUSY for short. Weird name. It's a mathematical theory which unifies the fermions and the bosons. Okay, and it states that for every fermion there should be a boson equivalent, and vice versa. So for every fermion there's a corresponding boson, like a partner, and for every boson there's a corresponding fermion. And these counterparts, these partners, they're called sparticles. Okay, particles but with an S at the front. How does it work? How do we name these particles? Well, for the boson partners, for fermions, you put a S at the front, okay, a prefix S. For the fermion partners, for bosons, you put an eno at the end. So, I'll show you how this works. It's quite simple. Simple naming system. Suppose you've got quarks and leptons. There's supersymmetric partners, as they're called, squarks and soleptons. Okay, these are the boson equivalents, if you wish, of the quarks and leptons. Let's get into the actual naming of these particles. So suppose you've got an up quark, you've got an electron, suppose you've got a tau neutrino, you've got a photon, you've got a gluon, and you've got a Higgs. Okay, let's find their supersymmetric partners. How do we do that? How do we name them? Well, up quark, so up quark is a fermion. Okay, if you put an S at the front, it becomes up squark. An electron, it's a fermion. Its boson partner is selectron. Tau neutrino is the fermion. Its boson partner is called the tau neutrino. Not that I can pronounce it. Photon is a boson. Its fermion partner is called a photino. A gluon, it's a boson. Its fermion partner is a gluino. Don't know if I spelled it correctly. Higgs, it's a boson. Its fermion partner is the Higgs xeno. Okay, and that's how supersymmetry works. So for every particle, fundamental particle in the standard model of particle physics, there's a corresponding partner. In other words, the universe is believed to have double the amount of particles. And I should also mention that we typically write, let's say, the electron like this, okay, or just with an E. Its counterpart would look like this. It's got a tilde. The symbol here is called a tilde on top of the E, and that signifies supersymmetric version of the electron. Why do we like supersymmetry? Why do I like it as a particle physicist? Well, it does something pretty amazing. So, yeah, according to the standard model of particle physics, and the Big Bang theory itself, if you go back in time, you find that the forces of nature don't really unify. So let's say there's electromagnetism, there's the weak nuclear force, NF, strong nuclear force, let's say we've got these three forces, okay, and there's no gravity in the standard model. That's why there's only three forces here. They don't seem to come to converge at a point. They don't really meet up at a point, but supersymmetry fixes that problem, and what you get is a beautiful convergence when you add particles to the universe. It's a very powerful mathematical theory. This could be a great thing to add for your, if there's a HSC question based on limitations of the standard model of particle physics, you can talk about this. It fails to unify the forces in the early universe, and also it hasn't yet predicted experimentally supersymmetry with what we have at particle accelerators.